Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss the concept of effect of friction in suction and delivery pipes on indicator diagram. In our previous lectures, we have discussed regarding the indicator diagram of reciprocating pump. So basically we know that in the indicator diagram, it represents the comparison between the stroke length and the pressure head. So the stroke length will be in the x-axis. So this represents the stroke length. And in the y-axis it represents the pressure head. So for the other things we have already discussed. So now we'll see the effect of friction in suction and delivery pipes, and that is going to represent in the indicator diagram. So this is the pressure head. Okay, so before going to discuss this diagram, let me remind you that in the previous lecture we have identified the equation for the effect of friction for the suction and delivery pipes. So what we identified previously, we got the value of HFS. Okay, so HFS is nothing but the effect of friction. Okay, the effects of friction in the suction head. So this equation we got actually 4FLS divided by 2ds into G. This is the equation came from, I'll write the equation actual equation is the loss of head or loss of effects due to the friction, or we can say this is the loss of head due to the friction. The equation is, we know that is Darcy-Weber's equation 4FL V square divided by 2dG. Actually this is the equation. So when you're writing the S, that means for the suction pipe. For the suction pipe means here also we need to mark it LS, that means the length of the suction pipe, and this is the diameter of the suction pipe. So this is the initial equation, and this equation we know that we have derived already Darcy-Weber's equation while in the losses of energy, and this is the equation for the major loss or losses due to the friction. Okay, so from this we have identified the value of velocity V. Okay, the value of velocity V, and this is actually we got, that is capital A by small a into omega r into sine theta. So this is the formula for the velocity. Okay, and this velocity value we need to put it here. Okay, so here also, as we are mentioning here S, so here also we can mark it AS, area of the suction pipes. Here this is the velocity of the suction pipe. So here I'll put the value of V. So we'll get here capital A by small a S, and this is omega r, and this is sine theta. So this whole square. So this is for the HFS. That means the loss of head due to friction in the suction pipe. Similarly, I can write the loss of head due to friction in the delivery pipe. So delivery pipe, I'll mention it HDS, or I can write HFD. FD, friction at the delivery pipe. So this one also we can write the same way. We can write the formula 4FLD divided by, this is 2DD 2G, sorry 2G already written, so G into, again we can write here A by AD, and this is omega r into sine theta whole square. Okay, so these are the two equations we already derived previously. Okay, and this is the effect of friction on the, or loss of head due to the friction in the suction and delivery pipes. Okay, so now if you see this equation, so from this equation it is clear that HFS and HFD, okay, this will be a function of theta with parabolically. This is the function with the theta as a parabolic. So how it is a function of parabolic? So this is our, we can say HFS is what I told you, that loss of head due to the friction at the suction pipe. So if you remember that how the work is happening in the reciprocating pump, so just I'll show you the crank movement. So the crank is to here at the initial position, it is there, and this is the center point of this circle. So this one I can mark it O, and this is our A point. Okay, so that means when the pump supposed to start at that point, okay, our crank is to like this. The crank is to situated like this, and this is our R, suppose radius, crank radius. Now when the pump started working, so the piston will be started moving from left to right. So from when it started moving, so this crank will be also started rotating angularly here like this. Okay, so half of the revolution completed, and in the half of our revolution we can mark it C point, and before C point we can take another one point. This is B, like means the crank rotated with an angle of 90 degree here, so half of the part completed. Again remaining half is completed in the forward direction. So this forward direction is nothing but suction stroke done. So suction stroke, what I told you, that head, this HFS is what? The loss of head due to friction in the suction pipe. So due to the suction stroke, the suction pipe will be there, in the suction pipe will be there. So this is half revolution completed. Similarly, one more revolution will be there, that again will start from C point and it reaches to the A point through the D point here. So I can give a D point here. So what I mean to say here, at the starting of the position, the crank is at 0 degree angle. At the B point, it is at 90 degree angle. And at the C point, it is having 180 degree angle. D point, we are having 270. Again, it will back to the 360 or 0 degree angle. Okay. So this is the movement of a crank in the reciprocating pump. So why I told you this parabolic function? Because you can see, as I told you this, if you take this is a forward direction or suction stroke, it is moving a parabolic, creating a parabolic function here. So this is the angle. This is the theta angle. Again, if you see, this is our backward direction, reverse direction, that is our delivery stroke. So this is our delivery stroke and this is our suction stroke. I hope you understand. So similarly, the same thing was given here. This is our stroke length. So stroke length is nothing but the distance of piston in the cylinder. Okay. So during the suction and delivery strokes, we can say the pressure head inside the cylinder will be changed. Of course, it will be changed. So it will move from 0 degree to 180 degree. Okay. Now suppose the first condition, we'll consider the first condition at the beginning of the suction or delivery stroke. Either it may be suction stroke or delivery stroke, the theta will be 0 degree. Okay, the theta will be 0 degree. Now if I take this is our suction stroke, then this will be 0 degree at this point. Sir. Now if I take this is our reverse direction or delivery stroke, I can take this is our 0 degree. Again, I can come back here like this. So during the delivery stroke, so the theta equal to 0 degree at the beginning of the suction or delivery strokes, what about the value of sine theta? Because in the equation, if you see, sine theta is there. So sine 0 degree. So sine 0 degree. So sine 0 degree equal to, we know that this is 0. If this is the 0 value, then for this condition, our HFS and HFD both will be 0. HFS and HFD both will be 0. Now let's come back to this diagram here. If you see the diagram, as I told you, this is our stroke length. Now see, this is the diagram we got. This ABCD diagram, if you see, this is the diagram for the ideal indicator diagram we got. After that, we have discussed about the acceleration effect in the suction and delivery pipes. Okay, and that we have represented in the indicator diagram also. And that was a little bit inclined we got here. If you remember, in the previous lecture we have discussed, we got an inclined line like this, and here also an inclined line. Anyway, for the effect of friction, if you see what I got here in the first condition, HFS and HFD both are 0 when the theta equal to 0. The theta angle is 0. Now if you see at the A point, starting point of this, okay, the stroke length, if you consider this is our total stroke length here, okay, I can consider here. So at this point, theta equal to 0. So A point, we can mark it here, starting point 0. Again, if you see HFD point, I can, if I starting from here, suppose, then this is also 0. You will start from 0. Now the next one, second point I'll consider. Second point what? At the middle of the suction and delivery strokes. So middle of the suction and delivery strokes, let me remind you, if you forget, actually, the pipe used to like this. Okay, and this is our so reciprocating pump is there. This is our water storage, and this is the actually cylinder. This is the cylinder is there, and inside that we have the piston. Okay, and this piston is connected through a piston rod to this connecting rod. Again, the connecting rod is connected to the crank here. Okay, the crank is going to rotate here like this, as I'm telling. And here this piston is moving from left to right. When it will be at the starting position, this is. Okay, next, Next condition what will tell, when the theta equal to 90 degree. So theta equal to 90 degree means at this position it is 0 degree. Now when it will rotate to here, the crank will be rotated half of this. Obviously this piston will be moved up to this point. So half of this completed, and this will be like, you know, the crank will be like this, it will be connected to the crank. The connecting rod will be connected to the crank here. So the position will be like this. So at this position, again we need to find out what is the value of sine 90. So sine 90 degree, that is 1. So if you got the sine 91, then obviously you can put the value in this equation. So what we'll find here? So HFS, okay, we'll get like 4F LS, and divided by this is ds into 2g, and here in the bracket we'll write a by as, and here omega r similarly square. And similarly for the HFD, just you put the d value here, that's it. So this is for the second condition. So second condition, what I told you, that theta equal to 90 degree. Similarly, so 90 degree, that means we got some value here. At least we can get some value here at this point for the suction pipe. Similarly, for the delivery pipe also, we can get some value. Let me write this otherwise. 4F LD by DD into 2G divided by A by AD into omega R square. So here also we'll get some value. Now let's check it at the end of the suction stroke or delivery stroke. At the end of suction stroke or delivery stroke. So this is the starting point. Now see how this parabolic form, like, you know, parabolic curve you got here at the suction and delivery stroke, you can say. Now at the third point, when I will consider that theta equal to 180 degree, theta equal to 180 degree at this point, that means one part is completed here. Again, if you start from here, again one part completed here. Forward and backward, or suction stroke, delivery strokes, that we can consider. So when theta equal to 180, again we need to find out the value of the sine theta. So sine theta sine 180. So sine 180 equal to 0 again. Okay, that means again what? HFS and HFD. Again both are 0 here. So if you both are 0, again now see here theta equal to 0 degree, we got sine theta 0. Theta equal to 90 degree, we got some value. And theta equal to 180 degree, again it's coming to the 0 point. That means half of the revolution completed, we got again the same value. So if you see the variation of HFS and HFD, it's showing a parabolic in nature. That means here some value is there, so we can get some value here. So this much distance is nothing but HFS. And similarly, here the distance what we got here, that is HFD. Okay, because some value is there in this. And this nature, we can say this is a parabolic in nature, and that we need to represent in the indicator diagram. Okay. So how to find out this area? This if you see this AGG dash and BGG dash at the suction pipe. So the area of this AGB at the suction side, and other side if you see, that is CHD. Okay. This is another side is CHD. So the area of these things we need to calculate. So we can write area of AGB can be calculated. That is the length. What is the stroke length is there? The stroke length, that means AB into, I'll write 2 by 3 GG dash. So that is nothing but area equal to 2 by 3 base into height. So this is the base, this is the base, and this is the height. So how much height we don't know. So this one we can write again. So you can write the area of AGB. You can write this is AB. So AB plus what I can write? The stroke length, that is nothing but L. And here I can write 2 by 3. GG dash is nothing but, see GG dash how much is there? That is HFS. So the same thing I can write here. This is the area of AGB. Similarly, so here HF is equal to, here HF is equal to this one we need to consider. Okay, this HFS value is nothing but this one. Okay, now again we need to find out the area. Similarly, we can find out the area of CHD, correct? So CHD again we can write same thing the same way. We can write 2C into, sorry, CD, the stroke length distance. Actually the what formula I told you, that is nothing but 2 by 3 into base into height. Okay, this is the formula. So here also same thing, CD into 2 by 3 into HH dash. So same thing we can write area of CHD equal to nothing but CD into 2 by 3. You can write HFD, the height of this HS dash. So just put the value here. You can get L into 2 by 3, and this is HFD. So this is the area of CHD. Okay. So here also, what is the value of HFD? So the equation what I have written here, that is the value of HFD here. So I hope you understand this effect of friction in suction and delivery pipes on indicator diagram. So previous class we have discussed about the acceleration part. So in the acceleration, if you remember, just we got this equation like how we got the value, like this we got the line. Okay. And here also we got the line like this. Okay. So that also we got through the exact equation. By solving that, we got this. Like this we got the equation for the acceleration, effect of acceleration in the suction and delivery pipe. Now for the friction, we got a parabolic in nature. Now you see, so this can be calculated by from this equation, from the friction loss of head due to the friction. And yeah, I hope you understand. Still, if you are having any doubt and query regarding this, you can give a comment on the comment box. Thank you all.